Hi, students. In this note set, we're going to take a look at bonding. In our last unit, we talked about what makes an atom and where are the electrons within an atom. Now that we've got a sense of the individual atoms, we're going to ask the question, how do the atoms interact with each other? First of all, you might be a little bit surprised to know that even the most advanced chemists don't have a definitive idea of what a bond is. There's really no way to define it very succinctly. The best we can do is to say that a bond is the altogether the sum total forces that hold groups of atoms together and makes them function as a unit. But even that definition isn't a super good one. And that's all we can come up with so far. So if any of you end up as chemists in the future, maybe you can work on this definition for the benefit of all. We know this much. When atoms bond together, they have an energy that is lower when acting together as a group than if the atoms were separated. And that has to do with, well, the idea of entropy. Entropy is disorder. In any spontaneous reaction in the universe, entropy always increases. So what that means is the sum total of the available energy is always going to be lower at the end of a spontaneous reaction than at the beginning of it. And the same idea holds true for forming a bond. You're releasing energy when you form a bond. Okay, let's take a look at a couple of atoms. We have two hydrogen atoms. H is the symbol for hydrogen. And let's say that we have a proton in the nucleus, and the electron, if it's neutral, it's only going to have one electron for hydrogen. And it could be anywhere in this distribution or scatter plot of dots. Now, remember, that's all the locations of the one electron that could be there. And they're just showing it all at the same time in this one image. So here's one hydrogen atom. Here's another hydrogen atom. Now notice, since the electron distribution for either of the two hydrogen atoms is not anywhere close to the opposite atom, then those two hydrogen atoms are sufficiently far apart to have no interaction, meaning they could be miles and miles apart, and it would be no difference than their current distance, which is maybe even a fraction of a centimeter. And keep in mind, atoms are extremely small. But as we bring the two hydrogen atoms closer and closer together, so now we're bringing the hydrogen atom on the left towards the hydrogen atom on the right, and now the electron of one atom can feel the presence of the other atom. Now, think about what it's feeling at that point. And when we say feeling, we're talking about electrical attraction and repulsion. So let's consider the electron of the hydrogen atom on the left side. It's a negatively charged particle. Electrons are all negatively charged. Opposite charges attract. So that electron is both attracted to its own nucleus, which is positive, and to the other atom's nucleus, which is positive. But at the same time that it's experiencing that attraction to the opposite atom's nucleus, it's also experiencing a repulsion from the opposite atom's electron, because electrons are negatively charged. If you have two of them, well, they would repel each other. There's a certain distance that is called the optimum distance, where you achieve the lowest overall energy of the system. In other words, you've released as much energy as you can. And if you bring the nuclei closer than that optimum distance, there's repulsion going on, not only from one electron to the other, but also from one proton in the nucleus to the other proton in the opposite nucleus. And it's also maximizing the attraction from one atom's electron to the nucleus, the attraction to the other atom's nucleus. Let's graph this. Uh, in just a minute, we'll take a look at a graph. When we talk about how long a bond is, we're talking about the distance between the two bonding atoms' nuclei, the internuclear distance. And that length is where the lowest energy is found when the bond forms. And at that particular bond length or distance between nuclei, two things are true. Number one, the attractions from one atom's electron to the opposite atom's protons are maximized. And secondly, repulsions between the proton of one atom and the proton of the adjacent atom, and between the electron of one atom and the electron of the adjacent atom are minimized. Maximize attraction, minimize repulsion, and you have your optimal bond length. Now let's take a look at this graph. We're plotting on the x-axis internuclear distance. So as you go to the right, we're increasing the distance between the two nuclei, starting with 0 on the very, very left. And going, and keep in mind, atoms and internuclear distances are very, very small. So we're using units of nanometers. On the y-axis, we have energy plotted with a release of energy being a negative number and an absorption of energy being a positive amount of energy. If you push the nuclei really, really close such that they're touching each other, the energy spikes way high. It spikes so high that you can't actually get them to touch each other because the electrostatic repulsion would be too great. And then if you were to, let's say we look at the very right edge of this graph, if you separate the two atoms very far apart, at some point they're not going to feel the presence of each other, and it's as if they would be miles apart. So that energy would be close to 0. But if you look at this graph, there's a dip down or a trough, where the energy is lowest, and there's a certain internuclear distance that is optimum. In the case of a hydrogen molecule where there's two hydrogen atoms bonded together, it just so happens that the optimum bond length is 0.074 nanometers. And when that bond length is achieved, the energy released in forming the bond is, the negative means the energy is released, it's 458 kilojoules for every mole of hydrogen molecules formed. And there's a whole bunch of different bond energies and bond lengths that you could look up. You'll never be asked to memorize these, but it is helpful to notice some trends. Let's take a look at a carbon to carbon atom single bond. The bond length is 154 PM, stands for picometers, 10 to the negative 12 meters. The bond energy associated with a carbon to carbon single bond is 347 kilojoules per mole. Compare that to a carbon to carbon double bond. Well, the bond length is shorter, 134 picometers as compared to 154 for the single bond, and the bond energy is higher, 614 kilojoules per mole. What about a triple bond? Carbon to carbon triple bond. Aha! Bond length is even shorter. So students, notice that if you double bond or triple bond a couple of atoms, the two nuclei in the bond are going to be drawn closer to each other. Think of it as a bond with a really good friend as compared to a bond with an acquaintance. You might say with your really good friend, you're very close. Well, in the case of atoms in a bond, that's literally true. You're closer. The two atoms are closer to each other. And we can say that the energy in the bond is higher. There's more energy invested. And we see that same trend playing out with a carbon to oxygen single bond as compared to a carbon to oxygen double. A carbon to nitrogen single bond is compared to a double and a triple. Same trend is shown for multiple bonds. Okay, now why do some atoms form certain types of bonds where other atoms don't? And how can we even begin to talk about the amount of energy that's associated with a bond? Well, to answer that, students, we have to introduce a concept called electronegativity. Electronegativity is the ability of an atom in a molecule. So it's already got to be in a bond before we can talk about an atom's electronegativity. The ability of an atom in a bond or a molecule to attract shared electrons. In the picture here, they're showing an atom, and these are the electrons that are smaller than the atom, of course, and it's as if the atom is exerting a magnetic force of attraction. Well, different elements have different levels of electronegativity. In fact, we have a whole ranking system. Every element has a unique ability to attract electrons, and we're going to rank them just like we would rank a GPA. GPA runs on a scale from 0 to 4, with 4 being the highest. And if we take a look at the elements on the periodic table, here are their electronegativity values. Where's the highest one? Way up here in the right corner, fluorine. And you might wonder, okay, I see all of the major elements here. Yeah, we neglected the intertransition metals, or actually they kind of threw them in here. They just said, they're going to be in some range. They all have similar electronegativity values, and they're quite small, around electronegativity value of 1. But you might notice there's no noble gases. Why are there no noble gases on this chart? Well, an atom's electronegativity refers to its ability to attract electrons in a bond. Well, noble gases don't bond. They don't even form bonds. And so we can't even rank their ability to attract electrons within a bond because they don't even form them in the first place. Thus, the rightmost column on this chart is actually the halogens, group 17, and there are no noble gases. Okay, the most electronegative element, fluorine, king fluorine, with a perfect 4.0 GPA, or electronegativity ranking. And just after that, oxygen with a 3.5. And then in third place, it's a tie between nitrogen and chlorine, both of which have a 3.0. So those 4 elements, Fonkel, F-O-N, and Cl, are the 4 most electronegative elements. That's something that's helpful to remember. I encourage students to remember that Fonkel as being the most electronegative elements, because it determines how electrons are shared in bonds. Okay, we've identified where the most electronegative elements are. They're all in the upper right corner. Where are the least electronegative elements? Well, they're way over down here in the lower left corner. Francium and cesium are tied at 0.7. Closely behind that, we have rubidium and potassium with 0.8. And then sodium and radium and barium all with 0.9. So anything with an electronegativity value of less than 1 does not attract electrons very well in a bond. In fact, whenever any of those elements are in any kind of a bond, it's going to be an ionic bond because they're so weak when attracting electrons. Is there a trend within groups? So look in the vertical columns. Where do you see the highest electronegativities? At the top. In every single group, you're going to see the highest electronegativity values at the top of the group, because that's where the smallest atoms are found in a group. How about within a period? Periods are the horizontal rows. In moving from left to right, generally you'll see higher electronegativity values as you move to the right. So further to the right means you're going to have more protons for having the same number of electrons, or at least the same principal. Okay, now that we know something about the trend of electronegativity for individual elements, let's take a look at molecules. Now, one thing I should say, you do not need to memorize electronegativity values whatsoever. They'll always either be given to you, or if you just remember that the greater electronegativity values are found further to the right and higher up in the periodic table, in other words, towards fluorine in the upper right corner, then you'll be able to pick out the most electronegative element in a bond in almost every scenario. And if it's not a scenario where you can easily pick it out, then it's not a fair question. Let's consider water, H2O. Now, oxygen is one of the four very electronegative elements. It's the O in Fonkel. And on the periodic table, oxygen is directly next to fluorine. So oxygen is one of the most electronegative atoms out there. And in water, oxygen is bonded to hydrogen, which doesn't have an especially high or an especially low electronegativity value. It's right about in the middle. So if we're considering which atom in that covalent bond between oxygen and hydrogen draws the electrons towards it more strongly, it's definitely the oxygen. So if you look at this sketch of the water molecule, it's showing positive charge around the hydrogen and negative charge around the oxygen, because the electrons within this covalent bond are drawn more strongly, and are found therefore more often around the oxygen side of the molecule than around the hydrogen side. And that has a lot of profound implications for a collection of water molecules. If there are different electronegativity values for atoms in a bond, then there's going to be an unequal sharing of the electrons. Chemical bonds in which electrons are shared unequally, we give the name polar to. Polar meaning there's a positive end and a negative end, or a positive side and a negative side. And whichever atom is more electronegative is going to be the negative side of the bond. And the reason for that is because electrons are themselves negatively charged particles. And if they're negatively charged particles, the atom that they hang out around more often will acquire a negative charge. Now, we should say it's not a full-fledged negative charge and positive charge. Full charges are shown rather in ionic compounds. We're still sharing the electrons, but we call it a partial negative charge around the oxygen and a partial positive charge around the hydrogen. So if the electrons move away from the hydrogens, there's going to be a resulting positive charge due to the lack of negatively charged electrons. The greater the difference in electronegativity, the different types of bonds that we find. So it's all about differences in electronegativity. If you take two really electronegative atoms, like take two fluorine atoms, if they're bonded together, then the difference in electronegativity between the atoms is zero. They would share the electrons in the bond perfectly equally. But take a look at this chart. If the difference in electronegativity in the bonding atoms is zero, then you have a perfectly equally sharing of electrons. We call that a nonpolar covalent bond. If there's an intermediate level of difference in electronegativity, we call it a polar covalent bond, a bond where there's some unequal sharing, but it's not so unequal that one of the atoms becomes completely positive and the other atom becomes completely negative. That would occur in an ionic compound. So when there's a very large difference in electronegativity, you have an ionic compound. Now, think of this, students. We've said in an earlier unit that if you bond a metal with a nonmetal, you get an ionic compound. If you bond two or more nonmetals, you have a covalent compound. Well, that makes perfect sense. On the chart for electronegativity values, the metals are found on the left side, and those are the lowest electronegativity values. The nonmetals are on the right side. So if you pair something of low electronegativity on the left side of the periodic table to something with high electronegativity on the right side, like a metal with a nonmetal, you'll get an ionic compound. Here's a nice way to visualize it. Let's say you have two bonding atoms which have the exact same electronegativity values. So the easiest way to picture this is if you have two atoms of the same type in a bond. So this is like a diatomic molecule. Two atoms of chlorine bonded together will completely equally share the electrons in the bond. If there's a difference in electronegativity, then you have a polar covalent bond with the electrons inhabiting the space around the more electronegative atom. And you can see, do you see the little squiggle sign here? That squiggle sign means partial negative charge. And the opposite side, where the electrons are not found as much, is a partial or squiggle positive charge. So hydrochloric acid, or HCl, is an example of a polar covalent bond. And then if you take it to an extreme, if there's a complete transfer of electrons from a metal ion like sodium to a non-metal ion like chlorine, then you'll get a completely positive charge and a completely negative charge. Now, the atoms are still attracted to each other, but not because of a sharing of electrons. They're attracted to each other because now they have acquired opposite charges. Okay, let's talk a little bit about the symbols, that some of which we've seen so far, that we use to represent electronegativity differences. This squiggle is a lowercase Greek letter delta. I'm sure you've seen the uppercase Greek letter delta in math class, like delta y over delta x for the slope of a line. Well, that looks like a triangle. Lowercase letter delta looks like a figure 8 that isn't quite completed. It stands for partial charge in chemistry. The side of the bond with the greater electron ownership, it would be the atom that has a higher electronegativity value, is designated as squiggle negative or delta negative, partial negative charge. And the opposite is true as well. The side of the bond with less electron ownership, that is a lower electronegativity value, is designated delta positive or squiggle positive. There's another symbol that's important for us to know about. An arrow that has a plus sign on one side and an arrowhead on the other is always going to point from the positive end of the bond to the negative end. So the arrow will look like this. It's a normal arrow with an arrowhead, but then there's this extra slash. The extra slash almost looks like it's forming a plus sign. And if you put the plus sign on the atom that is the positive end of the molecule, and the arrowhead pointing to the negative end, you'll have it oriented properly. So let's take a look at hydrochloric acid one more time. Here's that arrow, and between hydrogen and chlorine, chlorine is closer to the upper right corner of the periodic table. It's right next to fluorine, and it's one of the four most electronegative elements, funkel. The arrow points from the hydrogen side of the molecule to the chlorine side, and we see the squiggle negative around chlorine and the squiggle positive around hydrogen, indicating partial negative and partial positive charges. Okay, let's try a sample problem here. Here is a chart of electronegativity values. Let's see if you can arrange the following bonds from most polar to least polar. To do this, you're going to look for the differences in electronegativities. So notice, of all three bonds here, nitrogen to fluorine, oxygen to fluorine, and carbon to fluorine, they all involve fluorine. On the periodic table, fluorine is in the very upper right corner, and you can see the three atoms that they're asking you to consider bonded to fluorine right next to each other. So oxygen's here, nitrogen's here, carbon's here. They all have different electronegativity values, but they're all bonded to fluorine. So you can think about this. What's the difference between 4 and 3.5? That would be the smallest difference of the three bonds that we're looking at. The largest difference would be the difference between 4.0 and 2.5. So the most polar bond would be the one with the biggest difference in electronegativity. So that gives us this ranking. Carbon to fluorine is the most polar, followed by oxygen to fluorine, followed by, oops, hold on. Now it goes nitrogen to fluorine, followed by oxygen to fluorine. Because oxygen to fluorine is the lowest difference in electronegativity. Okay, let's try this one. Chlorine bonded to chlorine, boron bonded to chlorine, and sulfur bonded to chlorine. They all involve chlorine. And we're looking at atoms that are, one of them's really close to chlorine, like the sulfur. One of them's pretty far away, the boron. And then we're asking you to consider chlorine bonded to itself. Well, students, if any atom is bonded to itself, guess what the electronegativity difference is? 0. There's no difference in electronegativity if you've got two atoms of chlorine bonded to each other. Immediately after that, we've got chlorine bonded to sulfur, where there's just a difference of 0.5. And there's a slightly bigger difference between boron and chlorine. Now, what if you didn't have the chart of electronegativity values? Just go by distance from chlorine on the periodic table. Since sulfur is exactly next to chlorine, they're right next door neighbors to each other, they would, in all likelihood, even without these values being shown, just by looking at a normal periodic table, you could say, they're going to have the pretty similar electronegativity values. At least sulfur will be closer in electronegativity to chlorine than boron would. So that gives us this ranking. The most polar bond is boron to chlorine, followed by sulfur to chlorine, and then the least polar would be chlorine to chlorine. Okay, so far, when we've talked about electrons in the distribution of negative charge within an individual bond, we've only been considering two atoms. But now I want you to consider multiple atoms. We're going to give a term bond dipole to refer to unequal charge distribution within a single bond. And we're going to give the term dipole moment to refer to unbalanced charge distribution within an entire molecule. So we're looking at collections of atoms, more than two atoms with a dipole moment, and just two atoms with a bond dipole. One thing, this has to do with physics, which is not something we're going to get a ton into, but bond dipoles are vectors, which means they have both a magnitude, like there's a numerical value to them, and there's a direction, and the direction actually does matter. When you consider bond dipoles, they add as if they're forces. In other words, you've got to consider the direction in which they're acting in order to get the molecule's dipole moment. Let's take a quick look at some examples. Carbon dioxide consists of a central carbon atom and two oxygen atoms that are oriented 180 degrees apart from each other. We'll talk about molecular shapes coming up in the next week or so. But trust me for now, this is what a carbon dioxide molecule looks like. The oxygen atoms are exactly 180 degrees apart from each other. And yes, oxygen is more electronegative than carbon. So if you consider the two bond dipoles, they're going to be oriented exactly like this, where the negative charge is pointing outwards towards the oxygen atoms. Each of the two bonds within this molecule are polar bonds. But because they're oriented exactly 180 degrees apart from each other, they cancel out. There's no dipole moment for the molecule because the bond dipoles cancel out. Okay, let's take a quick look at a couple of other molecules that also show bond dipoles, but may or may not have dipole moments. Let's return to water. Remember, water is H2O, and the particular shape of water is important to considering its dipole moment. We will get into Lewis structures and molecular shapes shortly, but for right now, you can trust me when I say that the water molecule has this shape. It looks kind of like a boomerang, where the hydrogen atoms are on one side of the oxygen atom, and they're not exactly opposite each other. Now, we've already seen how we can indicate partial charge with the lowercase Greek letter delta, and we would put a partial positive charge around each of the hydrogens and a partial negative charge around the oxygen, because oxygen is the more electronegative atom and draws electrons towards it more strongly than hydrogen does. As a result, the two covalent bonds in water, if we were to draw arrows over it, would point towards the oxygen atom. So two bond dipoles with the plus sign on the hydrogens and the arrow pointing towards the oxygen. Now, when considering the entire molecule, we have to consider how those bond dipoles would add together. If they're both pointing towards the oxygen atom, then they're both pointing at least partially downwards, at least as it's oriented in this picture. But the two bond dipoles are pointing in opposite directions left to right. The bond dipole on the left is pointing slightly to the right. The bond dipole on the right is pointing slightly to the left. So the left-right nature of the bond dipoles cancel out, and we're left with just a dipole for the molecule called the dipole moment pointing downwards. So bond dipoles in water cancel out left to right or side to side, but they both point downwards. And so the water molecule does have a dipole moment, which means the molecule has a positive end and a negative end. That has profound ramifications for how water behaves chemically. The fact that it has a positive end and a negative end explains a lot of water's unique properties. But if you contrast that with carbon dioxide, which we had seen just moments ago, the two bond dipoles cancel out. Carbon dioxide is not a polar molecule. And so it's not going to behave the way water does in a collection of molecules. Let's take a look at a couple of others. Sulfur trioxide. Now, you might say, oh, geez, I wonder which atom, sulfur or oxygen, is more electronegative. And one way to do that is to look at a chart of electronegativity values. That's a fine way to do it. The other way to think about this is, geez, I remember the four most electronegative elements, Fonkel, fluorine, oxygen, nitrogen, and chlorine. And since oxygen is one of those and sulfur is not, I know that oxygen is going to be more electronegative than sulfur. But if you didn't remember that, that's fine. Here's oxygen with a 3.5 value and sulfur with a 2.5 value. So oxygen is the more electronegative atom. Now, when we take a look at this molecule, the shape matters. I don't expect you to be able to come up with the shape of the molecule just yet, but we will shortly be able to do that. Sulfur trioxide is a triangular molecule within a plane. It all exists in one plane. There's a central sulfur atom indicated yellow here, and three oxygen atoms oriented 120 degrees apart at pointing to the vertices of a triangle. And since all the oxygen atoms are more electronegative, we show greater electron ownership around the oxygen atoms. One way to represent that is with this kind of a map called an electrostatic potential map, where the reddish coloration is greater electron density and the bluish area are the lower electron densities. But because of the triangular shape of the molecule, the bond dipoles are all oriented away from each other and thus will cancel out. Once again, kind of like carbon dioxide, Sulfur trioxide has polar bonds, but there's no dipole moment for the molecule. One last consideration, then I'll turn you loose here. Carbon tetrachloride. Again, chlorine is one of the Fonkel elements. So right off the bat, you might say, oh, since I remember Fonkel, I can identify immediately that chlorine is going to be the more electronegative. But if you didn't remember that, that's okay. You can just consult a chart of electronegativity values or even a periodic table and ask yourself which element is closer to fluorine. And since chlorine is just one step away from fluorine, you could say, okay, it's going to be more electronegative than carbon. The shape again matters, and I do not expect you to be able to come up with this shape yet, but we will shortly. In a week or two, we'll be able to draw this. This molecule shape is called a tetrahedron. It's a pyramid with a triangular base, and all of the bond angles are the same, 109.5 degrees apart. So if chlorine is the more electronegative atom, we can indicate the bond dipoles with the arrows pointing away from the carbon and towards the chlorine. We could also draw an electrostatic potential map showing chlorine having a high level of electron density and the carbon showing bluish or lower levels of electron density. Once again, we have polar bonds. Now, it's not superpolar. The difference in electronegativity between carbon and chlorine is only 0.5, so they're not. It's for the most part pretty darn equal sharing of electrons, but it's still not perfectly equal. And so there is a bond dipole and a polar, four oppositely oriented polar bonds in the molecule, but they all cancel out. So the molecule itself does not have a dipole moment. It's a nonpolar molecule which has polar bonds within it. The three-dimensional shape of the molecule matters. And for right now, that's all I want you to know is that bond dipoles can orient in space so as to cancel each other. And the actual shape of the molecule plays into that consideration.